Welcome! Today we'll look at a group of specific materials that everyone makes use of every day. These are metals. Metals and minerals flow through our society. Metals are all around us. With current technology, living a metal-free life means no smartphone, no television, no car, no plane, no transport whatsoever. Well, unless you buy the newest wooden bike, of course. We eat metals too. Our bodies need a bit of metals, such as zinc and selenium. Without it, you will die in the end. Fortunately, such crucial metals normally are present in our diet. Nice to know, you might think, but there is a little more to it. These metals come from somewhere. They don't fall from the skies. Well, actually some do, but that's another matter. Metals originate from the Earth's crust. Mining operations, often in remote regions, dig out metal ores from which the metals are extracted by the metallurgical industry. This has been going on for millennia. Remember, the Bronze Age is indeed a while ago. The thing is, metal ores are not infinite. Just like oil and gas, there is a limit to metal reserves in the Earth's crust. Take zinc. Some experts believe that zinc will become scarce within the next 1 or 2 generations. For quite a few other metals, similar scenarios are predicted. So we need to be careful not to spoil metals and keep them available as much as possible in the cycle. The aim of this video is to get an idea of how microorganisms, especially bacteria, can help us to do so. Biorecovery of metals from waste streams by using microorganisms can contribute to this purpose. You might think that metals and microbes are a poor match for closing cycles because microbes are organic and metals are inorganic. Actually, most metals in the periodic system show some form of interaction with a wide range of microbes. Let us take a look at some of these interactions that are useful for biorecovery of metals. For that, I'll return to the metal zinc. In industrial waste streams, zinc is often present in its ionic form, zinc 2+. Very often, such wastewaters also contain sulfate. Both zinc and sulfate remain dissolved in the water if nothing is done. Interestingly, after sulfate has been reduced to sulfide, it can facilitate the precipitation of zinc. Let's have a closer look on sulfate reduction first. Sulfate is a so-called terminal electron acceptor for numerous kinds of bacteria. Remember that many catabolic reactions in nature are redox reactions, so with an electron donor and an electron acceptor. For us humans, oxygen is the terminal electron acceptor, while we can use sugars, for example, as electron donor. Sulfate-reducing bacteria use sulfate as electron acceptor, and they can use materials like ethanol or hydrogen as electron donor, but also many other compounds, even sugars. As you see on the slide, hydrogen sulfide, or sulfide for short, is the end product of biological sulfate reduction. Sulfide behaves very different to sulfate. It rapidly reacts with many metals, also with zinc. It then forms a very insoluble precipitate, zinc sulfide. The zinc is precipitated to very low levels, and metal-free water remains. In addition, the zinc sulfide is not a waste. It can be reused as a source of zinc production. You could say it is a renewable zinc ore. It's nice to know that microorganisms can do this. But can we really make use of it? Does it work in practice? Look at this tall vessel that you see over there. It is a 500 cubic meters bioreactor, in which there are trillions of sulfate-reducing bacteria, all producing sulfide. That sulfide is indeed precipitating zinc. The resulting zinc sulfide as feedstock can be used as feedstock for the metallurgical industry. And in the end, zinc metal is produced that can be used for all kinds of products. Now, let's have another look at another example to show how versatile microorganisms are. Some can carry out the reaction you see on the screen. This reaction involves the element selenium. And just like zinc, selenium is a compound that humans need in micro quantities. Without selenium, we will become ill. Selenium is also present in some wastewaters. Biorecovery of elemental selenium can thus contribute to securing selenium availability for farmers. And via agricultural products, it also remains available to us, consumers. The reaction shows the biological reduction of dissolved selenate, with lactate as electron donor. The product of this reaction is elemental selenium. Elemental selenium is a solid, so also in this reaction, the metal goes from a dissolved state to a solid state. It involves what we call a phase transition. This makes separation easier, because we just have to separate the solid from the water. So, what should you take home from this video? The conclusion is that the circular economy has to involve the recovery of metals from waste streams. Recovery with the use of microbes is a promising way to achieve just that. It can recover the metals in a solid form that facilitates separation from waste streams, watery waste streams, and moreover, the metals are recovered in a form that is reusable or recyclable. As you have seen, this idea is already applied in practice to some extent. However, work is underway to keep metals in the cycle. The potential of microbes to recover metals needs to be explored and researched further, so we can deal with more metals in a cyclic way. Innovative companies can bring these technologies to the market, and they do. Besides technology development, public and political awareness also needs to be raised on the need to recover metals. Too few people actually realize that we will run out of metals, such as zinc, and that can be in the next century. Industries need to be encouraged to recover metals from their waste streams instead of wasting them. We can't simply afford to wake up one day and find out metals are depleted. We must wake up now.